Good morning, all. So the experiment is the susceptibility of a paramagnetic material by Quincke tube method. So the first part is already uploaded in the website. So I hope you all have seen the video, right?
Yes, sir.
So we are doing the second part, that is the experimental part. Okay. So four parts are there in this experiment. So first, the preparation of the sample, right? So we'll use manganese sulfate. So this is the powder, manganese sulfate, and we'll prepare the solution with the help of the beaker and this specific gravity tube. So this specific gravity tube, it has 25 ml. The volume of the specific gravity tube is 25 ml. Okay. So I hope you have seen the manual. So first, what we'll do, we'll measure the mass of the beaker, right? We'll measure the mass of the beaker, and then putting the sample, that is MnSO4, and we'll make the solution with the with water, right? And then we'll use this specific gravity tube to measure the density of the solution. So we'll measure the mass of the specific gravity tube. That will be called I think W1, and then we'll put the water and measure the mass again. So the 20 ml we'll use, the full volume we'll use, and that will be called W3, right? Specific gravity bottle plus water, that is W3. And finally, the which are prepared, the samples will put in the specific gravity bottle, and we'll measure the mass of the bottle with the solution, that will be W2. So the density of the solution, rho, that would be rho water multiplied by W2 minus W1 over W3 minus W1, right? So W water at 4 degree it is 1, right? But at room temperature we can take is near about it is 1. So we'll take W water as 1, and then measuring the value W1, W2 and W3, we can determine the density of the solution. Okay. And the masses of the beaker and water, and the masses of the beaker plus solution, that is water plus the salt, the MnSO4 salt, that masses will be used in the calculation part. Okay. Now the temperature is the temperature is required to determine the Curie constant. So we'll note down the temperature. Okay, the room temperature. The third part of this experiment is to determine the height difference in presence of magnetic field. Okay, so now the tube is visible. Tube is visible. This tube.
Yes, sir.
Yes, sir.
Yes.
Yes.
Okay. So it has some U-shaped tube. It is called Quincke tube. It is specially designed tube. The one part of the one arm is of the capillary, right? So the one part, the diameter is very low, and the other arm of this tube, the diameter of the other arm is wider than this one. Okay. So I'll put the solution. I already put the solution here. So in presence of magnetic field, the height will increase, okay, for the paramagnetic substance, and the height will decrease if the sample is paramagnetic one, right? But in this form, in the wider which a wider part, wider diameter, this the height difference will be negligible there. Okay, so only the height will be increasing in the smaller diameter part. Okay, so this is King's tube. So we'll use the tube to hold the sample, and this this level would be put in the middle of the electromagnet. So this is the electromagnet. This is the electromagnet. It is connected to this cable to the constant current power supply. So here we can increase the current, and gradually the magnetic field will also increase in this space. Okay, and the magnetic field will be maximum in the middle, exactly middle of this electromagnet. Okay, we can adjust the arms. We can adjust the arms by this. Okay, so we can adjust the arms. So if these two poles, one is south pole and one is north pole, so if the two poles are come closer, then the magnetic field will obviously increase. Okay, and if the poles are being part apart, okay, then the magnetic field at the middle will decrease. So I'm going to place this tube exactly in the middle. So I think the level is in the middle between the two poles. Okay, so we'll see this level with the help of traveling microscope. So this is the traveling microscope, and we can adjust the height by this knob. So the basic principle is the principle of a screw gauge. Okay, so the rotation part, it has 100 divisions, and with the full rotation it will move to 0.1 centimeter. Okay, so you can calculate the least count of this instrument. Now we will move this one. Okay, we will rotate it and we'll adjust the height. So there is a crosshair here. We can see the crosshair, and we will have to adjust the level. So it will be inverted and it will be like this. So the top of the crest will be the at the middle of the cross section of the crosshair. Okay, so this is the focusing knob. So we'll focus through this. So is the level visible?
No, sir.
Okay, just do it. So you can see, right? It is hazy, but you can realize it.
Yes, sir.
Okay, okay. So it will look like this. So I'm switching on the constant power supply. So we have to ensure that it is in the minimum position. So the current is 0 now. Okay. Now we'll increase the current in a few steps. Okay. So the current is now 0.5 ampere, around 0.5 ampere. And we'll see here the height change of the height, the rise in the height of the tube. Okay. So it is very difficult to show it again and again. So we'll assume that it is moving. Okay. And we'll increase it gradually in few steps. So in 0.5 ampere, in 1 ampere, 1.5 ampere. In 2 ampere, and we'll note down the height from this scale. Okay. Now the height is changed as we increase the current. Okay. So what I have to do, we have to adjust the height with the help of this microscope, that this traveling scale. Okay. We'll rotate it and it will come to the, suppose it has initially it was in that position. Okay. Now it has been increased to this. So we'll adjust the crosswire. We'll adjust the crosswire and we'll take the crosswire in this position. Okay. So initially, suppose it was in this position. So we'll measure through the scale, through the linear scale and the rotational scale. Okay. And then after reaching, after the increase of the height, so again we'll measure the value of this height by these scales. Okay. And then we'll differentiate it, how much height it has gone or it has rise. Okay. So the next part of this experiment is to calibrate the magnetic field with the current. Okay. So I'll minimize the current. I'll minimize the current to 0. And I'll remove the samples. And we'll use the same stand to calibrate the magnetic field. So this is the probe. The probe is visible. So this is the probe. Okay. So we'll put in this stand. The probe will be put in this stand like this, like vertically. Okay. So that the maximum magnetic flux can move from the north pole to the south pole of the electromagnet. Okay. And it will detect that, and it will measure the magnetic field corresponding to the current. So again we'll put in the middle, exactly middle, where the samples are taken. because at that position magnetic field is needed, right? Then we will switch on the Gauss digital Gauss meter. So here in Gauss, the magnetic field will be noted, and this is the zero adjustment. So at current 0, there should not be any field, right? So this is the adjustment. So this value is the minimum to be adjusted. It is not being it is the minimum value, because if we rotate in the anti-clockwise, then the value is increasing. Okay. So we'll place the probe in the different position. 15 Gauss, 15 multiplied by 10. So this is the 10 factor. Okay. So if we put the knob in cross 1, that will be the exact value. That is the value, the zero adjustment value is 156 now. Okay. Now, if we take this knob in the cross X position, then the actual value is the value shown multiplied by 10. So the value shown here is 15, right? So the actual value is multiplied by 10. That is 150. Okay. So now we'll increase the current. .5. Now the value is 139 multiplied by 10. Okay. So 1390 Gauss. So we'll note down that value. Again, in the 1 ampere, we'll measure. So the value is 278 multiplied by 10. That is 2780. Right. Now it is 1.5 ampere. The value is 4090 Gauss. At 2, it is 5460. At 2.5, 680 into 0 into 10, that is 6800 Gauss, 6.8 kilo Gauss. At 3 ampere, the value is 807 multiplied by 10 Gauss. So likewise, we'll measure at a certain values in the interval of 0.5, or you may take at 0.25. Okay. So these values will be noted, and we have to plot these values, and in the x-axis it will be current, and y-axis it will be the magnetic field. Then we'll calibrate it, and while we put the samples, we don't know the value of the magnetic field, okay, at that particular current. So but the magnetic field is needed at the particular current. So we'll calculate what will be the value of this of the magnetic field at that particular current. So from where we'll get? From the calibration curve. Okay. So now we have the age value corresponding to a current, and corresponding to a current we have the height difference. Okay. So initially it will be noted, and the difference we have to take. Suppose initially it was 2.01. 001, and then after increasing the current, maybe the value would be some 135, right? So the difference, that will be the age, that will be the small age, the difference in height. Okay, that we know at a particular current, and the magnetic field is also known from the calibration curve at that point of at that point at that point of current. Okay, so finally we'll make the graph as a function of h and the magnetic field square, and it will be a straight line, and then from the slope the value of chi, the magnetic susceptibility, can be calculated from the graph. Okay, thank you.